Example 14-5. Spring calculation. A spring stretches 0.15 meter when 0.3 kilogram mass is gently attached to it. That's figure 14-3b. The spring is not then set up horizontally with the 0.3 kilogram mass resting on a frictionless table. It's in the figure 14-2. The mass is pushed so that the spring is compressed 0.1 meter from equilibrium point and then released from the last. Number one, we're going to determine the spring stiffness constant K and angular frequency omega. B, we want to determine the amplitude of horizontal oscillation A. C, we find out the magnitude of maximum velocity B maximum. D, we have to also find the magnitude of the maximum acceleration A, max of mass. E, now we will check the PD of the T and the frequency F. And F, the displacement X as a function of time, and G, the velocity at T is the 0.15 second. So you can quickly just draw the picture of this problem. So that helps us understand how the situation actually appears in this problem too. So you have a single spring attached to the wall. That is like this. And there's the object, which is 3.3 kilogram attached to this spring, so that the object, that is M, vibrate, oscillate along the equilibrium position X equals 0, and that spring produced the power, the force based on the Hooke's law, which is X Fx, and that is the mass M produced force downward based on the gravity. The gravitational force exert downward force, the drag that mass downward, so that displacement X should be expressed in the function in time out of the simple harmonic oscillation motion. So from that, from the given condition of this problem, your X naught is the 0.15 meter, and the mass is 0.3 kilogram. So number one, we have to first calculate spring constant K, or stiffness, which is F divided by displacement. So here, F is mg. Only force applied to this spring is the gravity. So F should be placed with mg, and now it goes with the x naught. So here mg is the 0.3 kilogram times 9.8 meter per square second, and x naught is 0.15 meter. From that, spring constant K should be the 19.6 Newton per meter. Using that, K and omega, K and mass M, you can find angular frequency omega, or angular velocity omega, which is square root of K over M. So plug that K value into this square root, and that should be 19.6 Newton per meter, and M is 0.3 kilogram. That it lead to number of 8.08. The one invert second. So with Using those numbers, you can estimate also magnitude, amplitude of original oscillation. So A is 0.1 meter. Compress the 0.1 meter, and then C, maximum velocity should be omega A. So the omega is 8.08 hertz for inverse second times 0.1 meter. So that leads to the answer of 0.848 meter per second. That's the maximum velocity. So number D, question D. So F is ma from the Newton's law. So the maximum acceleration should be force divided by mass. So the force is k times maximum displacement A out of the Fuchs law, and m that should be divided by mass m. So that is 1.96 so k actually 19.6 newtons per meter, and A is 0.1 meter by the 0.3 kilogram. So the answer is 6 point acceleration, maximum acceleration should be 6.53 meter square second. And E, the period T is 2 pi square root m over k. So here 2 should be 2 pi times square root of 0.3 kilogram, and denominator should be 19.6 Newton per second. So that should be 0.777 second of that period, and the frequency is, as you know, 1 of t. So that frequency is 1.29 hertz. And now F is the asking the displacement x as a function of time. So motion begins at the point of maximum compression. T equals 0, x is minus a, which is minus 0.1 meter. So x should be minus a cosine omega t. Here, cosine theta. So basically, here t is 0 and x is minus a, which is minus 0.1 meter. So basically that lead to that displacement equation like this. So you know the cosine theta should be minus cosine theta minus pi. And if you move that minus sign to left hand side, then minus cosine theta, the same as cosine pi of theta. So basically that is same as cosine theta minus pi. If you apply this relationship, this formula, then x should be minus 0.1 meter cosine 8.08 t. So you plug that minus sign into this cosine function, then that should be 0.1 meter cosine 8.08 t minus pi. So that initial phase value should be either minus pi or minus 180 degree. The question G, we have to estimate the velocity at 0.15 second. So all you need to plug that the number of time into the velocity function out of the displacement equation. So that is V is first derivative of displacement in time. So that is omega A sine omega t. So you plug all those number omega and the maximum displacement A, and again the omega plug back into this formula, and then replace t with the 0.15 second. Then velocity should be 0.808 meter per second sine 1.21 radian. So that lead to the answer of G, which is the 0.756 meter per second. Okay.